Hello everyone. In this video we're going to talk about optimization algorithms in TensorFlow. So if you looked at my previous videos, you see sometimes I use like the Adam optimizer, sometimes I use SGD, and there are a lot more, okay? So here I have 12 of them, and I show you the algorithm for all 12. Now I'm not going to discuss all 12 because each one of them can easily take a video or two just to go through all details of that. So what I'll focus on in this video is the stochastic gradient, and then probably MRSProp and the Adam. Okay, these three that are used a lot, especially Adam and SGD, and a lot of the other ones. They are kind of a variation on the Adam, like N Adam, this Ada delta, kind of, not exactly. Adam max is definitely. This one by Google, FTRL, is a quite bit different one, and as it says, it's a family of algorithms. There is Ada factor, there is Adam with weight decay, decoupled weight decay called Adam W, there is Ada belief, and there is Lion. Okay, so among them I would say Lion and this FTRL are very complicated, and they need a very long video to explain them. So again, that's not my goal. So the stochastic gradient descent, okay, remember at the end of the day, all of these algorithms are based on the gradient descent, which is moving in the negative gradient at any point to go down the surface. The problem with this method is when it gets to a local minimum, it can get trapped there, okay? So if this is like the surface of your cost function, and you're starting here, so you go downhill until you get to there, and then if you just work based on gradient, here you should stay, because if you want to move more to the right, now you're going in the opposite gradient direction, not negative gradient direction. So you get stuck there. Okay, so there should be some additional thing to push you forward and say, hey, you might have reached a local minimum, but keep pushing forward and see if you can go further down. Okay, and one of the things that is used in the literature a lot is this guy here called momentum. So momentum means what? Means, hey, if you reach here to this local minimum, and now ideally based on the gradient, you should not move anymore, right? Because in either direction you move, you are going in the positive gradient direction, not negative, right? And you're not going downhill anymore. So this one says, hey, before getting there, remember you had momentum, you were moving, you had some changes. So now that you are reaching there, guess what? Use some of that previous momentum and don't stop there. And that's what you see in nature, right? If I release a ball up here, and it comes down here, when it reaches the bottom of the hill, it's not going to stop. It's probably going to go a little bit uphill, and depending on how much this uphill is, maybe the momentum is sufficient to pass over the uphill and go down to the next downhill. Okay, so this is inspired by nature, rolling a ball down on these surfaces, and the fact that momentum does not just disappear. Okay, so what they did is, they say the change in any parameter, right? If you call the parameter x, remember when we did gradient method, we said x at iteration t is what? Is x at iteration t minus 1, correct? And then minus the change in it, or plus the change in it, you might call, and that was negative some learning rate alpha times what? Times the negative gradient of the cost function, right? If you move in that negative gradient direction, then you should be able to update the parameter. Okay, so this was the simple gradient descent, which, as I said, has problem of being trapped. And this is, by the way, this is like your, you might call this delta x. So now this delta x, that was simply a constant learning rate times a gradient. Now we say no, it's not as simple as you think. It comes from what? It comes from the gradient times the learning rate. So this learning rate here in this formula is the same as alpha, and this L prime here is the same as this del of G. That's the same thing. But I also add to this some extra thing. What is it? I add another constant term times the previous change in the parameter, and this is your momentum, okay? So my current change is affected by the gradient as well as the previous change, okay? And this P here is a factor less than 1. And the smaller it is, the smaller the effect of momentum, the bigger the effect of what? The learning rate, okay? But clearly you see that it makes this delta x with respect to the momentum to kind of exponentially decay. So, and that should be like that because we don't want momentums that were like so many iterations before to affect the current one. We just want the previous one to affect it. So here we add the momentum term, okay, to keep it rolling. Or if it's like the surface is kind of like a flat plane like that, and again we get the ball rolling, it comes down here. Now ideally it should stop because the gradient is 0, so it should not change. But if we keep it pushing because there is some momentum down the hill, if we say, hey, keep that momentum and go down, maybe you get what? Maybe you get to another downhill. Maybe you get to a global minimum. So this momentum method is really useful for keep moving, okay? And in many algorithms, they say that this P is equal to 1 minus alpha. Okay, so you say the sum of these two parameters is equal to 1. One of them is alpha, one of them is 1 minus alpha. And the thing is, this alpha, which is the learning rate, in SGD, we consider it constant. So we say this alpha is what? This alpha in the SGD method is a constant. Now we can create a function, as I showed you in previous videos, for rate scheduling. So we artificially and manually change this alpha, but this method is not adaptive. Okay, this optimizer is not adaptive. The learning rate is constant in it. While all other optimizers, as I mentioned for you here, all of these other optimizers that I mentioned afterwards, they all manage this alpha. They change alpha based on how the optimizer is doing. Okay, so they are a little bit more adaptive compared to this stochastic gradient. So this stochastic gradient is like the first and the most well-known algorithm, and it can do fine except for some scenarios. And one of the disadvantages or shortcomings of this, not shortcoming, a disadvantage of this algorithm is when you have big data sets, this algorithm performs a lot of redundant computations, which makes your optimizer versus epoch to have lots of fluctuations. Okay, so if you plot that cost function versus epoch, remember that J that we did versus epoch, okay, this method makes it go with a lot of what? With a lot of variations, especially because alpha is also what? Constant. So if we can make this method go a little bit smoother, again, we make this P bigger, it kind of make it a little bit smoother, but not perfectly, okay? Because it does a lot of updates for each parameter in each epoch. And so the goal is to remove some of these huge computations and all of these minor oscillations and these fluctuations. So what are some of the other algorithms? Let's talk about some of them. So one method is called Adagrad, and my goal is not to go through that completely, but just want to tell you. Adagrad stands for Adaptive Gradient Algorithm. Okay, so as the name says, it's using gradient as every other method, and it tries to be adaptive. So it tries to change the learning rate and do it for individual features. So what does it mean? It means some of the weights in your data set, they have different rates than the others, and this is really good. So some of the weights in the neural network, they use a different alpha than the other ones, depending on how they are changing, okay? And this could be really useful, especially when you're dealing with the sparse data sets. And a lot of inputs are missing, and so some of your weights could go down very, very slowly and update very slowly, so they might benefit from a larger learning rate, and some of them are changing much faster, so you might reduce the learning rate on them so they don't start overshooting. Okay, and here, again, if you look, this is the update equation for that, where this guy here is that gradient term. Okay, so W is like one of the weights. This L is the same as J. And this is basically the gradient. So you see it moves in the negative gradient. This eta here is the same as alpha that we have, but it's not a constant eta. It's also always divided by something. Okay, so this whole thing here is your learning rate, really. It's a constant divided by a square root, and the square root does change. So your learning rate adapts. Now, this alpha here that you see, this alpha total, or the summation of gradient square, is sum of the individual gradient terms in the previous iteration squared over all of the weights. So this is sum of all squared gradients. And when you take the square root of that plus some epsilon, then you can use it as the denominator. Okay? Yes? So you see your individual gradient component is divided by the square root of sum of all gradients, individual gradients squared plus epsilon. What is this epsilon for? This epsilon is a positive number to ensure that if for any reason at any point this alpha is 0, it can, when, as I said, you go to a flat surface like this, your surface of the cost function becomes a plateau like that, you can get 0 gradient, and now here you have a number divided by 0. To avoid division by 0, we use this small epsilon number, so the denominator is never 0. Okay, so this is called Adagrad. Another method we have is called MRSProp, or root mean square propagation. So root mean square propagation is an exclusive version of the Adagrad. So we just saw Adagrad. Now this is another version of the Adagrad. And instead of letting all of the gradient accumulate for momentum, it only accumulates gradient in a specific window. The good thing is, of course, the learning rate is adjusted automatically. And if you look at here, if you look, your parameter update theta here is the same as W in the previous one. And the reason these notations are all different because I got them from different sources. So each one has their own notation. What matters is you know which one of these guys is the parameters, the weights and biases, which ones are the momentum or anything else. So here this theta is like the W or B. And you see the way it is updated is very similar to the previous one. If you look at that, you see that gradient is divided by that square root multiplied by eta, very similar to that. Now, instead of this alpha, here we have this term V of t. And what is V of t? V of t is basically what? Is the summation of gradient squared, but not all of them. If you look, this V of t is updated through this recursive equation, where it comes from a gamma, a constant, times the previous V of t, and 1 minus gamma times gt squared. You see, so this makes a moving average window, or a running average, you might call it. And it's not really average, it's weighted average. Okay, so you see the effect of the current gradient is 1 minus gamma, and the effect of previous ones is gamma. Well, here, if you break down this alpha is like what? Is like summation of all of these what? Gradients from the initial sometime I, the initial time, to the current t. Okay, so this alpha here is simply like alpha of t minus 1 plus current gt squared. So if you want to write it in the same notation as this previous one, it's simply like that. You just accumulate sum of all previous squared gradients to the current one, and that is summation of all the gradient squared from beginning to the current time. But here I'm not doing that. I multiply each one of these by some weight. I multiply this by the weight gamma, and I multiply this by the weight 1 minus gamma. So I give each one of them a discount factor. Okay, so you see it's an adapted version of what? Adaptive and different version of Adagrad. That's all it is. And when you go through many of these algorithms, many of them are just like a previous one with some minor modifications, okay? It's not like each one of them started from scratch and developed something. And most of them, as you can see, in most of these algorithms, all of them are basically this guy, the gradient descent, plus some momentum or some adaptive learning rate, or both. Now, what is ADAM? ADAM stands for Adaptive Moment Estimation. So, this method, it utilizes the concept of momentum by adding fractions of previous gradients to the current one. The advantage of this method is it requires less memory and is computationally efficient for large data. Sometimes it might not converge to optimal solution. It adaptively calculates the learning rate, and for different parameters it has different learning rates. It does not need a ton of hyperparameters, and it also can work with noisy data and noisy gradients. So it is most of the time an optimizer of choice, but pay attention that it might not always go to optimal solution, but it can have lots of advantages. It's not super computationally expensive. It works with noisy data. It works with large data. It is adaptive. It also uses momentum. So that's why this method is a really universally accepted method for optimization. And many of these other algorithms, as I said, like NADAM, like ADAM Max, and this ADAM W, these are directly some modified version of this algorithm. So what is this algorithm? Now, it needs a little bit more than some like simple P or learning rate, okay? It needs a little bit more, but let's see how it does act on that. So what do you need? You need a parameter beta 1, which is a parameter you have to choose. You have another parameter beta 2. You need a learning rate. You need this epsilon to avoid division by 0. Okay, so these are the 4 parameters you have to choose in general for it. Many times you don't choose any of them, and the TensorFlow goes with these default parameters. You can change these parameters, okay, but these are the ones that are suggested. So what does it do? At the end of the day, the parameter update is very similar to all other algorithms. V at the new iteration is V at the previous iteration minus the learning rate, you might call it alpha, times something. Now, what is this something? It's similar to this Adagrad or this MRSProp. It is basically something divided by a square root times something else. So it follows this format, if you can look at it. Okay, right? Now that eta here is replaced by learning rate, and g of t over square root is now replaced by that v over square root of s plus epsilon, and epsilon is brought out of the square root. But again, it's not really a huge difference, except this parameter v and this parameter s. What are they? How are they going to be updated? So let's talk about them. What are they? So v is the momentum term, and s is the momentum square term. Okay? Yes? So basically what this method does, it kind of combines what MRSProp does by working on the square of the gradient, as well as what the basic SGD does by working on what? By working on a power 1 of the momentum. You see, the SGD uses power 1 of the momentum. Adagrad or MRSProp, they use power 2 or squared of the gradients. This method uses both of them. It's a combination of those two. So you see here, if you look, this is the SGD method, right? This is the SGD method, where this first order momentum method is updated by parameter beta 1, its previous iteration, and 1 minus beta 1 times the current gradient. This dl over dv, that is your g. Okay, so you see I'm running a moving average window for the first order momentum, and I'm also running a moving average for what? For the second order momentum. Then you need to do some extra compensation for them called bias correction. And when you have them, you finally put them in this formula. Okay, so it uses a combination of moving average first order and moving average square or second order momentum, and uses an update formula similar to MRSP method, right? And it just brought this epsilon out. So you need this parameter beta 1, you need this parameter beta 2, the discount factors or the exponential factor that you have in first and second order methods. You need this learning rate initial, and you also need this constant, and as long as this constant is a little bit bigger than 0, that's all you need. So this is Adam. Now the other algorithms, that there are lots of them here. As I said, there is 8 more to go. I'm not going to go through all of them. I just show you the overall what it stands for. I'll show you the algorithm or the pseudocode, and I pass on, because again, if I want to go through each and every one of them, it takes a lot of time and it needs several videos. So that's not my goal to go through all of them. My goal was to explain the first 4, as I said, and just basically skim through the rest of them. There is another method called NADM, which is called Nesterov Accelerated Adaptive Moment Estimation. So all it does, instead of the simple momentum method, it uses the method called Nesterov momentum. And it is good when you have noisy gradients or you have gradients with high curvatures, and it can learn faster, but sometimes, just like Adam, might not converge to optimal solutions, and it requires quite a bit of hyperparameters. So one of the bad things about this algorithm I don't like is it needs a ton of hyperparameters. Okay, and so I would rather try other algorithms with fewer hyperparameters than someone with all of this and then go there. But if you look at it, the essence of the idea is very similar. Look here, M is the first order moment, N is the second order moment. So M and N here correspond to V and S. That's the same thing. Okay, very similar. G is that gradient term, okay? right? So you see very similar terms, and then these two steps are for that bias adjustment that are a little bit different. And if you look, the update in the weight is exactly similar to Adam. Again, this epsilon is brought under the square root, right? So that's what it is. Okay, it's not like I would say the only step that is really different is probably this M hat where you adjust for bias compared to here, basically. So one of them is just like this, the other one is not like that one. Okay. Then we have AdaDelta or adaptive delta method, which basically, instead of the idea of a learning rate, it replaced it with an exponential moving average of square deltas, which is basically the same as these previous ones. The thing is, you don't need to put a default learning rate for it. Okay, that is good. The disadvantage is it is expensive computationally. And the other disadvantage is the first updates on this algorithm are very small or slow. So initially this algorithm, exactly opposite to many other ones, it starts slow and then gains momentum really. Okay, so keep that in mind. But the good thing is it has two hyperparameters. It just has a decay rate and a constant epsilon. Epsilon is now a big deal. What really you need is the decay rate for that exponential moving average. Okay, and you can see it here again. If you look at this equation is the same as what? The same as basically this n equation, right? Or it's the same as what? This s equation here. That's the same thing. That's the same thing, okay? No big deal, okay? And it is using the root mean square for updates, okay? And then it starts accumulating updates too. So again, I don't want to go through this algorithm, just want to tell you what it is and show you. If you want, you can look more into depth of this, find the paper and see what it does. Adamax, which is the Adam with a max norm or infinity norm, is just a variant of Adam. So it is just using infinity norm or max norm. It is a stable method and it does not need a lot of tuning on hyperparameters. And it's suggesting you some values to go for hyperparameters. So you see it has beta 1 and beta 2. We had in Adam, it has the alpha. And so it is really, an alpha is the same as what we had in Adam. We call it LR. That's the same thing. And it has beta 1 and beta 2. So these three, these epsilon is no big deal, as I said. It's just a small number. So it's very similar to that. The only difference you can see is the place that it is using an infinity norm. Okay? The place that it is using an infinity norm. Look, the first momentum update is the same as Adam. No difference. Okay? But this U term here, which replaced the second moment term in Adam, this U term here, it is coming from a max norm, and it is updated by a max norm. Okay, so the only equation that is changed is this n equation, right, in Adam, or this s equation in Adam. This equation is changed, and it is using a max or infinity norm of beta 2 times previous max norm and the maximum value of what? The current gradient. Okay? So that's all it is. It's not really very complicated. Now, there are other algorithms. One of them is called FTRL, or follow the regularized leader. This is made by Google, published by Google, and it has regularization terms either based on L1 norm or L2 norm. It can minimize cost function better, but depending on what weights you choose for those regularizations, it might lose its stability or at least become less stable and not converge to optimal solutions. So selection of the weights for the regularization to avoid overfitting is an important thing. And the important thing about it is not a simple algorithm, it's a family of algorithms. Okay, it's quite a bit complicated. And you see the output of it is the minimizer of the regularized cumulative past losses. And if you look at the pseudocode or the algorithm code, you see that you can barely understand anything from it. Okay, I mean, look at this output, the weight update, okay? Argmin of that. And so the way that you calculate all of these cumulative regulars past losses, this guy, calculation of that is not that simple. Okay, it has quite a bit of depth to it, but here again you might be able to find the algorithm and look into it, and that's not my goal. There are 4 other algorithms that I did not even talk too much about them, but I just show you their algorithm or their pseudocode. If you are interested, you can see all of them in TensorFlow. One of them is called Adafactor, which has this basically algorithm here. You can see that again, it needs some parameters. It needs alpha, right? It needs beta 2, correct? You can see that beta 2 it has, right? There is epsilon 1 here and so on. So it needs some parameters, epsilon 1, epsilon 2, correct? You see there are regularization constants. So this method also has regularization. Okay, it has the parameter rho that you have. It has d, correct? So this method really needs you to know what you're doing. And if I have to try something, I would go with Adam first or SGD first. I'm not going to get into all of these complicated algorithms that might sometimes marginally make any better results, or sometimes not. Many times even this basic Adam can outperform them. So there is not one simple magic recipe to tell you which one to choose. You have to try these different ones, see which one acts better. But here are some general idea. If I have to choose, I choose the ones with minimum number of hyperparameters. See how it does. And a method that adaptively changes the learning rate and the momentum. So Adam can do that. That's why I like Adam. The Adam is really powerful. Or maybe N-Adam, or maybe this Adamax. Okay, they have some hyperparameters, but not a ton. 3, 4, maybe max. 2, 3. But if you need a ton of hyperparameters, like this algorithm, look, this N-Adam, I said I would choose N-Adam, not really. I would choose, as I said, Adam and probably Adamax, not N-Adam. It has a ton of hyperparameters. So we have Adam W, which is decayed decoupled weight decay. It's called Adam with decoupled weight decay, or Adam W. And again, it doesn't have a ton of hyperparameters, so it has only 3 or 4, which is good. That could be a really good thing, so you might try that as well. There is Adableaf, and Adableaf seems quite a bit simpler, I would say. It has some updates for first and second moments, and it has some bias correction and updates, so it's quite close to Adam as well. And it apparently does not need a ton of things, and it tells you what to start. So I would say this method only apparently needs beta 1 and beta 2 and alpha and epsilon. So this method could be also a good choice. Now the last one is called Lion, or LOA, and this is a very complicated algorithm. It's nature inspired, based on what the ants do as far as I checked. right? Or lions. I saw both of them, ants and lions, in the paper. So here it's talking about lions, I guess. And it's based on how they work and what their males do, what their females do. And it's just a pseudocode for it, okay? There is no formula here. It's a very, very complicated algorithm. And this is going to be the last thing I would try, okay? So hopefully this video was useful to you and you learn some basics about the 12 algorithms that are currently available in TensorFlow. And in my next video, I'm going to talk about the different loss functions or cost functions. Thank you so much. I'll see you in the next video.